So now we're going to take a look at another puzzle or a different problem where the same thing has happened. It had image one has been rotated to create the second image, but now we have a triangle, so it's a bit more complicated. And so we're trying to find the center of rotation. And so where is it is really the question. Now, if we recall from the previous video, we were able to determine that any center of rotation would lie on the line of reflection from one point to another. But now we're dealing with a multitude of points, and specifically three really important points, the vertexes of this triangle. So the vertex at B, the vertex at A, the vertex at C. And so we have to figure out where they all went. And so while I could figure out how to get B to B prime by rotating 180 degrees around this point, it wouldn't be that big of a deal. Rotating the entire triangle is another story. Because if I were to, say, trace this triangle a little sloppily, that's really sloppy, let me do a slightly better job, and put my center of rotation where it needs to go and try to rotate it, we could probably get B to line up. In fact, keep going. B's there, yay, but nothing else is lined up. So that's not the center of rotation. Well, it works for B, it doesn't work for anything else. We have to get slightly more creative. But I'm just going to find a bunch of points that work for B real fast and kind of fake it for the rest of them. What I know, I'm going to leave that on there. What I know is that it has to be on the line of reflection. And I remember that lines of reflection have to be equidistant between the 2 points and perpendicular. And since the slope between these is down 4 over 2 or negative 2 over 1, that means my line of reflection slope has to be 1/2. And so that's my line of reflection. And I'm just going to draw it in real fast, carefully, after putting a bunch of dots on here. That's my line of reflection. And that will work for any point B. So my question is, how can I make A and C work? And maybe I could do similar things to find the collection of points that make A work and the collection of points that make C work. Having found this collection called a line of points that make B work, and maybe there might be something in common. So I'm going to leave you to think about that. I need you to pause the video and think and talk to each other. And hopefully you can find somebody who's in the same place as you and you guys can work together to try to figure this out. I'm going to come back with the answer and you're going to have to figure out what I did. So I found it. It's 2, 1. That is the answer. That's my conjecture. 2, 1 is the answer. And I think there's only one. Now, I could be mistaken about that, but my answer is 2, 1. So what I'm going to do is go ahead and grab this. It looks like it's linked together, so I'm going to turn that off and grab just the triangle. And you'll notice my center of rotation is at 2, 1. My red blob is kind of off a little bit, but my center of rotation was at and is at 2, 1. So what I'm going to do is I'm going to grab this and turn it, and voila, it worked for all of them. Now, how did I figure that? What did I do? I left a little bit of evidence on the page, so I want you to stare at it for a minute and see if you can figure it out. I'm going to come back in a little bit. You need to be staring and thinking, what did she do? What did she do? So what I did, I'm going to give it away now, is I found the center, 180-degree center of rotation for these two, which was right here. See how I have these little dots here to try to help you. And I drew the line of reflection for those 2 dots. And there it is, and that's where the black line met the red line. And then I checked it to see if I was right. I didn't actually do anything with the C's, but I could have done the same thing and found the center of rotation, found the other line of reflection and saw where they met. And I bet if I do for C, it's going to meet at 2, 1. And so it's where the lines of reflection meet. That's the center of rotation, which is why I believe there's only one. Now, if you want to come back with me when I get back to California and tell me, no, I found more, that would be awesome. I'd love to have a good, healthy dialogue about that. I found one. So Using the correct mathematical vocabulary, describe and illustrate your process for finding the center of rotation of a figure consisting of several image and pre-image pairs of points. I just did that. So you might want to, I don't know, back up the video and have me repeat myself because I'm not going to do it now and I'm not going to answer number 3, but I am going to answer number 4. Prove the following theorem. The perpendicular bisector of a chord bisects the central angle formed by the radii drawn to the endpoints of the chord. I don't know what that means, except for that I do. So we had the vocabulary list you went through yesterday, and there was a really good reason why we did that yesterday. Before I do anything else, I'm going to grab my compass and get myself a good circle here. And I want to know where the center is. That's why I'm using the compass. So I can find the radii, right? And so here's my going to be the center. And I'm going to draw a circle. There's my circle and there's my center. And so I need to draw a chord and 2 radii. That, what does it say? The perpendicular bisector of chord bisects the central angle formed by the radii drawn to the endpoints of the chord. So this is the picture. And supposedly, if I do the perpendicular bisector of that chord, I will also bisect the central angle. So let's remember what we talked about yesterday, or what you learned, is there's my chord, this is the chord, and this is the central angle. And bisect means to cut into 2 equal pieces. So I'm going to go ahead and do the perpendicular, bisect this chord using the perpendicular bisector construction, which you guys were at one point quite gifted at. So you should be fine. I'm just going to go like that. And this, you don't really need to be doing this. It would be helpful, but you can do a sketch of this construction instead of an actual construction, since the compasses are locked away in my hiding place. So there we go. Now I use the same radius as my circle, and so that's why it's going through the center of angle. It doesn't matter if I changed it, the same thing would happen. And so I'm claiming in the conjecture I'm trying to prove that this line that's the perpendicular bisector of this chord also cuts that angle into 2 equal pieces. So that's what I'm trying to say. So that's what the theorem's all about, this picture. So here's another version of this picture that I did a bit differently and much more carefully. And here's my proof that goes with it. So here we go. I said AM and CM are equal. So I've named some points. So A is a point on the circle and C is a point on the circle. B is the center of the circle and M is the midpoint of line AC. So I'm saying that these two are equal because it was a bisector. We know that we did the perpendicular bisector construction, so that has to be true. And these 2 angles here are equal because it's a perpendicular bisector, they're right angles, and therefore they're equal 90, and that's fine. I went with proving the triangles are congruent because that's where my brain goes. MB is congruent to MB because, hey, the reflexive property. And therefore the triangles are congruent by side angle side, because I've got side and angle and a side. And therefore the angles that I'm trying to prove are congruent, which are the 2 at B, are congruent by CPCTC. Now that's one way to do this, and it's what I'm going to do. I'm going to also scroll down and show you what else I did, which is down here at the bottom. And where's my movie thing? Cannot find it. Okay. I'm having issues, don't mind me. Lots of them. Okay. I like this. And this is my sentence that since ABC is cut into 2 equal pieces, it's also an angle bisector. The other thing I can do is fold this in half. Like if I fold this circle in half so A lines up with C, M is the midpoint, and you'll notice that the 2 angles at B, if you kind of visualize folding it, they have to be the same because AB and BC are both radiuses of the circle, which is really how I should have handled this, is, hey, those are both radiuses, duh, they're equal and by side, or something like that. But it's just really clear to me that those are the same. And you can come up with a different argument than my basic general geometric proof, which I know we aren't very comfortable with. But this is the idea, okay? So your homework tonight is to find centers of rotation. You'll notice those are points. I need you to give me at least 4 possible centers of rotation that work. And remember, there are 1,000 because there's infinitely many. So you need to find at least 4. Okay, I'm not going to do one of these. If you want to know how to do 1 through 3, you're going to have to back up to the beginning of the video and look at how I did the first problem. Then the same thing here. This is find the single center of rotation that was done to produce the image. And again, back up the video, watch the examples that I've already done for you and see if you can find them. And then here, this is from the warm-up, find circumference and area for the given circles. And again, back up. You'll notice in the warm-up when I demonstrated, I did not multiply by pi. My answers were 1 pi, 2 pi, 3 pi, 4 pi, etc. Because it's just easier that way. And so make sure you're doing that. Good luck, and we'll talk again. At least I'll send you another video again tomorrow.